This is AQA A-level Chemistry. It is the Year 12 topic, Introduction to Organic Chemistry, and this is video 3 in this series. In the previous ones, we've looked at some basic naming, and in this one, we're going to focus on structural isomerism, the different types of it, how to draw it, how to recognise it. As always, I'm going to recommend you pause and try the tasks so that you can see how you do, rather than just listen and hopefully take it in. So we are going to look at structural isomerism and the 3 different types of it. I'm starting off by giving you the general definition for structural isomerism. Structural isomers have the same molecular formula but a different structural formula. That same but different model is going to feed through all of the different definitions that we learn here. Let's put it into practice. Let's try and name and draw the 2 structural isomers of C4H10. So we know that 4 carbons is bute, so we're doing isomers of butane. But the first one is the carbon chain, 4 in a row. I've got my 10 hydrogens surrounding it. And how else could I do it? Well, if I can't have 4 in a row, can I do something where I have 3 carbons in an unbroken chain? Yes, I can, with a carbon branching off on the second one. So taking a look at the names, we've already discussed 4 carbons in a row, no side chains. I've drawn butane, but in this example, my longest carbon chain is 3, which means it's propane, but I have a methyl group coming off. So we're going to take a look at positional isomerism. Remember, structural isomerism, same molecular formula, but a different structural formula. When we break these down into the more specific definitions, we're saying what the difference in structural formula will be. So here, it's the same molecular formula, but the functional group is in a different position on the carbon chain. So you'll be familiar from GCSE with alcohols, and that's an OH group. What different isomers of alcohol could we make with a carbon chain length of 3? Well, let's start off by drawing out my carbon chain of 3, and I could put my OH on the first carbon, or I could put it on the second carbon. Once I've done that, I can fill in the remainder of the H's if I'm doing full display formula, and I then need to work out the name. Now they're both prop, they are single bonds only, so it's propan, and alcohol has a suffix of ol. But they can't both just be propanol, because this OH is on the first carbon, it's propan 1-ol, whereas this is on the second carbon, which makes it propan 2-ol. So they've got their own distinct and separate names. Now let's look at chain isomerism. Again, same but different. Same molecular formula, but the different arrangement of the carbon chain. We actually saw this in the example with butane, where we drew butane and methyl propane. Try this now to show all of the different chain isomers of pentane. So in the first instance, we've got 5 in a row, which is pentane itself. But we could then think, if I can't have 5 in a row, can I have 4 in a row? And I can, because I can take a CH3 group off my second carbon. So I get methyl butane. I don't need to number it, because if I put my methane on this carbon, I would have numbered from this end, and it would still be on the second carbon. Because there's no alternative methyl butane, I don't need to include the number. But can I go further? Is it possible to get the longest carbon chain of 3? Well, it looks like we can, because I can go 1, 2, 3 with my groups coming off. So I've got 2 methyl groups coming off, so that becomes dimethyl propane. Again, I don't need to number them, because if I try to move this CH3 to here or here, I'm actually extending the carbon chain and turning it into a butane. Slightly more complicated, how many can you find for hexane? So I can do my 6 in a row, and there's no alternative to that one. So I go to 5 carbons in a row, a carbon chain of 5. And on this, there are 2 options. I could have my methyl group on the second carbon or on the third, but I can't put it on the fourth because that is actually recreating what would happen if it was on the second. I would number from the other end. So I've got two options that are going to be based around pentane. Can I go any further? Well, I can go to those based around butane. And I can have both of my methyl groups coming off the second carbon, or I could have one coming off the second and one coming off the third. So I've actually got 5 different isomers of hexane. Taking a look through, this one is hexane, 5 in a row. For these, I have got 2 methyl pentane and 3 methyl pentane as my 2 options. And if I take a look at these, the names are going to go down at the bottom with asterisks. In this one, my longest carbon chain is 4. I have 2 methyl groups coming off, so that's dimethyl, and they're both on the second carbon. So that's 2,2-dimethyl, 2,2-dimethyl butane. And if I take a look at the second one, where I have got 4 carbons in a row, I have a methyl on the second, a methyl on the third. So that's 2 methyls, so it's dimethyl butane, but this time it is 2,3-dimethyl butane. And finally, we're going to take a look at functional group isomers. Now, there are very limited examples of these that you will learn about, and we'll look at more of those later on, aldehydes and ketones, for example, esters and carboxylic acids, but we're going to look for a functional group isomer of alkenes. So what would be a functional group isomer of but1-ene? Same molecular formula, different functional group. Well, my butene is C4H8. So I need something that's going to be C4H8, but it can't have a double bond. So we need to know that the functional group isomer of alkenes is cycloalkanes. And we put them into a ring structure. And we can see each carbon has 4 bonds. And there are 8 hydrogens. So this has the name cyclobutane. That takes us to the end of this video and takes us to the end of this topic. Thank you for listening. Goodbye.